Okay, I think we'll get started. So today we're talking about hydrogen bonding, and we've come off talking about intermolecular forces, which are generic forces between molecules for basically just being molecules. So if they're polar, then we might have a dipole-dipole interaction. But even if they're non-polar, we have induced dipole interaction. And that's not really directional. It's there is some geometry to it, but more or less any molecule will have an interaction with any other molecule in a very non-specific way. But there's a special category of intermolecular forces that are called specific interactions, and the most important of these is hydrogen bonding. So we'll talk a little bit about that today. Again, it's a specific interaction. Now, those physical chemists who study hydrogen bonding, there's a real continuum here, but what we're going to talk about today is what, if you were talking to anybody who, unless they're an expert in hydrogen bonding, if you're talking to them, what they would think you would be referring to when you talk about hydrogen bonding. And so this would be the hydrogen bonding that's included in your general chemistry book, whichever one you're using. And under those conditions, if we have an oxygen, nitrogen, or fluorine bonded to a hydrogen, that's electronegative enough to start pulling off a bit of that electron density towards the more electronegative atom. So this bond is polarized, and hydrogen doesn't have many electrons around it. So when that gets pulled, it's leaving this exposed partial positive on the hydrogen over here. Now, there's an angle dependence to this. So as another molecule comes in, if it comes in on the hydrogen side, right, so not the other side, but the hydrogen side, then if it has abundance of electrons, then it can hydrogen bond with that. So these are typically nitrogen, oxygen, or fluorine as well. And so just sort of most often when you're referring to hydrogen bonding, you're referring to hydrogen on an oxygen, fluorine, or nitrogen, and then bonding to an oxygen, fluorine, or nitrogen. Now, it's a little bit awkward to say which one's donating, which one's accepting, and you'll see different things in the literature. On the one hand, this would be considered the hydrogen bond donor, and this would be the acceptor, if we're thinking about it from the point of view of the hydrogen. So this is the one with the hydrogen. But if we're thinking about it from the point of view of which one's supplying the electrons to create this bond, then this would be the donor, and this would be the acceptor. Now, most often, I'm going to do the first way, refer to the donor as the one that is giving the hydrogen. All right. Well, we know we have to come in from the hydrogen side in order to make this interaction. And actually, we have to come in on some kind of restricted cone angle there. So we can't be making hydrogen bonds straight up and down like this. There also is an optimal distance here. That's a fairly broad potential energy curve there, so there's a little bit of range on that distance. But this is actually one of the ways that, like when they do encompassing studies and they go through and look at everything in the crystal database, researchers will look for those that have these angles that fall within the cone angle and the distances to say, oh, there must be hydrogen bonding going on here, or it's very likely there's hydrogen bonding going on here. And if it's outside of those, then it's not considered hydrogen bonding. So some of these big database studies and machine learning studies would key in on those aspects. Now, the thing about the hydrogen bond is that in this scenario with these guys, it is in between the weak physical interaction physical intermolecular force, stronger than that, but it's a very strong, it could be interpreted as a very strong physical interaction, or it can be interpreted as a very weak chemical bond. And this is what's made hydrogen bonding so ubiquitous in nature. It is easy to make and break hydrogen bonds, and yet they're stable enough to allow for quasi-stable setups. So things such as the double helix in DNA and ligands binding to proteins. We don't want strong chemical bonds there, because then the ligand will never unbind, the DNA will never unzip. But we want sufficient enough interactions so that the ligand binds enough to cause a change in the protein to maybe inhibit or enhance the effect of an enzyme or something like that. So biology has incorporated hydrogen bonding in evolution in many ways. So hydrogen bonding is essential for biological life. All right, so that's the hydrogen bond. Unfortunately, with hydrogen bond, there's not a lot of homework you can do here. There's a little bit, but primarily it's just telling yourself the story, looking at different cases where you might have hydrogen bonding or don't have hydrogen bonding. If you become very interested in this, then you can look sort of beyond these cases. But for most practical chemical applications, what you're looking for in an interaction is it a hydrogen on one of these atoms? So to finish here, let's look at a case study. This might be a better way to go, or a good way to go. And there's just an enormous amount of literature on hydrogen bonding. I'm just going to choose something from our own research group here. We did a lot of work with pyridine, and we look at some nonlinear optical spectroscopy properties of pyridine. That's not so important. What's important is we are able to see very carefully pyridine's vibration. Pyridine is this molecule right here. So it's a planar molecule. It has a nitrogen here that can hydrogen bond. It can be a hydrogen bond acceptor in the language of it will accept a protein. These hydrogens are connected to carbons, so they don't hydrogen bond. So the thing about pyridine, and it's a liquid, if you just take pyridine out of the bottle, there's no hydrogen bond going on because there isn't the ability to be a hydrogen bond donor, so it can't hydrogen bond with itself. But pyridine mixes with water, and it can then hydrogen bond with water. And I've highlighted here a water molecule in red here is the one doing the primary hydrogen bonding with the nitrogen on the pyridine. This water then is part of a hydrogen bond network, and I've got those waters in blue. But other waters around this pyridine are not involved in hydrogen bonding in the way we think about it. So there's no hydrogen bonding going on here or here. So that's just solvated by the water, not actually hydrogen bonding to the water. And so what our study was to see if we can characterize this hydrogen bond by indirect methods, by looking at its effect on the vibrations of pyridine. So we can look at the vibrational spectra of pyridine as a liquid, and we do this through our technique based on Raman spectroscopy, which we haven't talked about, but we will in this series, and then compare it when it's in water. So what does the effect of water have on the vibration? And we might expect that there's actually cases where the hydrogen bond is happening and cases where the hydrogen bond is not happening. Remember, hydrogen bond is very weak, so it's a fleeting bond in the liquid. It's made and broken. And same is true in water. Like this will make and break, because it's not a strong bond like the OH bond, but it will be transient and fleeting. So there will be times when the pyridine is not hydrogen bonded, and there'll be times when the pyridine is hydrogen bonded. And that should have different vibrational responses. The particular vibration we look at is something called the triangle mode, and that's just the ring breathing mode. The ring breathing mode is just when all these bonds stretch and contract together. So the ring just gets bigger and smaller, bigger and smaller. That's called the ring breathing mode. All right, so I'm going to go to the doc cam here. We'll look at some of the data from our work on this, and then kind of see this as a case study here. All right, so we'll be looking at this paper here, the effects of hydrogen bonding on the ring stretching modes of pyridine. And gosh, yeah, that was almost 20 years ago. It seems like just yesterday. These are some of my students, so they definitely were the ones who helped get these data. But there's, of course, a lot to it, and it's difficult when you're first learning the basics of science to actually be able to read scientific papers. And the goal then is, as you go through your training, you'll be better and better at reading papers. Now, with that said, I think you should try to find some papers. Don't be discouraged at all if you can't, you get through the first sentence and you have to look up 2 words. That's just the way this is. But the fact that you're starting to do that and starting to recognize words, kind of recognize things you've seen in either these courses or some of your other courses in science, that's always a good thing to do. And don't use it as where your primary learning will happen, but use it as a way to see 2 things. Use it the way to see what's going on in science. So read recent papers, but then just also how to read and write. You have to practice, and so you can practice as you're learning, as you're growing through your curriculum. All right, well, let's get to the data here. So I'm going to key in right away on this figure, and in this case, we were working in mole fraction, and we haven't calculated too much, nothing on the board here. I think there were some homeworks where there was some mole fraction. But you can think of mole fraction as just a percent chance. So if you scoop up one molecule out of the solution, what's the chance that it's water or pyridine? And so this XPY, that means we're talking about pyridine. We could also talk about X water, and there, of course, if it's not a pyridine, it's a water. So the mole fraction of water is 1 minus the mole fraction of pyridine. So up here, this is what we call neat or pure pyridine. And then we don't get all the way to 0 because we're looking at pyridine. But if we were to get to XPY equals 0, that would be the neat water. But of course, we wouldn't see any signal then because we don't have any pyridine. Okay, so here's this ring breathing mode. It happens about 990 wave numbers. And we can see right here that there's a very strong peak and only one peak there. Now, when we look down here at only 10% pyridine, we can see that this peak has moved, and it's right here. And then maybe we can see a little remnant of the peak there. But by and large, it's shifted all the way over. And what this is saying is that when there are 9 waters for every 1 pyridine, the pyridine is going to be spending almost all of its time hydrogen bonding. So what we can see here then is a basically fully hydrogen bond situation for all the pyridines in the solution. Now, as we go to some of these intermediate ones, we can see that this shifts even at a mole fraction of 0.7. Let's see, where's 7? There's 7. Just barely starting to get a little bit of a hump there, but almost always non-hydrogen bonding. So when there's 7 pyridines out of every 10 molecules, most of them are spending time not hydrogen bonding. And remember, pyridine can't hydrogen bond with itself. But as we start to get here, and even at 50%, so here's the 50% mark, we see that there's a little bit more actually hydrogen bonded than not hydrogen bonded. And so that tells us something. It tells us that the equilibrium between bonding and not bonding for that pyridine is shifted more to the product side. So it's slightly product favored. So if it's 50-50, then more often than not, the pyridine will be hydrogen bonded. Okay. All right. Well, let me look at another study here. This is still pyridine in water. And now what we've done is we've kind of figured out that, let's go back, I guess I'll go back to this figure. So we said 50% is a little too far. And then 60% isn't quite far enough. So 55%, or a mole fraction of 0.55, is about right. And so at room temperature, right here at about 20 degrees, we see fairly even peaks here, this peak and this peak. And that means that about 50-50 chance that the pyridine is hydrogen bonded or not. And what we did was we were able to control the temperature of our sample. And so as we raise the temperature, we see that we end up with a little shift to less hydrogen bonding. And when we lower the temperature, then we shift to a more hydrogen bonding. And that makes some sense because although we haven't talked a lot about the effect of temperature on things, temperature will tend to jostle the liquid around and disrupt that hydrogen bonding. And so if we lower temperature, it tends to promote hydrogen bonding. And as we increase temperature, it tends to decrease hydrogen bonding. And that's for all things. So in water, higher temperature, water spending less time hydrogen bonded with itself than at colder temperatures. Let's just finish with something a little different. And there's this table here that got from this reference right here. And this is it's interesting kind of thought experiment. It's if we keep everything else the same, but let's just either increase or decrease the effect of the strength of hydrogen bonding just in water. And what would happen? What would happen? And so what we see here is the percent change from the current hydrogen bond case, and then what happens if we were in a solution of 37 degrees. 37 degrees is typical body temperature, and so a lot of biological processes here are what are being looked at. So no change. Of course, here's where we have no change, and here's where we're stronger on this side, weaker on this side. And we don't need to talk too much about this, but dramatically, just a change of under 30%, water's boiling point would rise to 37 degrees C rather than 0 degrees C. This is interesting here. Just a small change really changes the pKw, and we'll talk about that in the next series, the Introduction to Physical Chemistry 2. And what this does, this would limit the range over which, up 3. Yeah, actually, it would increase the range over the pH scale. So that's kind of interesting. Would have an effect on that. So if I'm reading this correctly, then instead of pH running from 0 to 14, it would run from 0 to 17. Gases become less soluble, so that would have certainly impacted, just this very, very small change would have impacted early life on Earth for sure, and life and now. This is incredible here, just a 2% change, and there wouldn't be a temperature of maximum density. So water has a maximum density at 4 degrees. And then it gets less dense as it cools. And it's a unique liquid in that manner. And two consequences of that is turnover in lakes. So lakes, when the water gets close to freezing, that will sink, right, initially, but it doesn't freeze down here. Because it's less dense as it gets colder, then that less dense will stay on top, and we get this ice on top of the lake rather than down from the bottom. So all other liquids, the solid would sink to the bottom, but for water, it rises to the top, and so lakes and oceans would quickly just fill with ice from the bottom, rather than getting that ice layer on the top and keeping the water as a liquid below and allowing for life to continue through the winter. And then if we go in this direction, increasing solubility, and right here, just 18%, and water would be frozen at body temperature. And so big effects there in increasing. So the hydrogen bonding. Viscosity, so water would flow more like, although I think it would still not be quite like motor oil, but it would be harder to flow through things, more resistant to differential flow through various things. So a lot of interesting things happen here with the change in hydrogen bonding, and so that's another aspect of hydrogen bonding. So hydrogen bonding, a critical thing for life, a critical thing in chemistry, and so really important to learn about it. As I said, hard to practice with a lot of homework problems, but you definitely want to keep telling yourself the story of hydrogen bonding.